Hello and welcome to our tutorial video for Computer Science 330/Physics 306. This will be a short introduction to implementing multiplexer logic on the pink Z1 board. In front of us we have the diagram for a 4 input, 1 output multiplexer with 2 data select lines. We need 2 data select lines in order to pick between which data inputs will be connected to the data output. Here we have the multiplexer exercise. I've created a bit of code that is to be run on the pink Z1 board in Jupyter. So I'll go through the code and then we'll incorporate some video output of what's going on the board. So first we import a couple of packages from the pink library. First in line 1 we import the Logic Tools overlay. That's the class, not the actual file. And then from Logic Tools, we also import a class called Waveform. From Python, we import sleep, and we set a constant equal n equals 16. Then we import the actual Logic Tools bit file using the Logic Tools overlay class. That's going to set up the processing layer and the programmable logic layer to handle what we're about to do. You can think of this as the step where we actually program some of the firmware in the programmable logic, and then we further program it with our specific tasks below. Um, Now here we create what looks like a wave DROM object, but it's the more general term is wave JSON, and wave DROM uses JSON syntax to generate the same waveforms that we will in this example. There is also a Wave DROM tutorial on the pink Z1 boards if you need a refresher course on how to use Wave DROM. We begin with a group called Signal, and then there's a couple of subgroups within Signal. There's the stimulus group and the analysis group. Let's talk about the stimulus group. There are 6 outputs being created here, bit 0 through 3, and then 2 data select lines. Bit pattern out 0 through 3 are piped to the digital I/O pins D0 through D3, and they have the following pattern. You're going to see this picture in gory detail below. On clock cycle 1, D0 is given the output of high, and then on clock cycle 2, D1 is high, clock cycle 3, D2 is high, and clock cycle 4, D3 is high. And that pattern is repeated, so you see these diagonal patterns of H's, and that's just because the data lines of the pattern generator have to take turns as they're sent into the multiplexer. Otherwise, we risk losing signals. If we're trying to send 2 highs at the same time, you can only select 1 line at a time. The analysis group is meant to just observe D0 through D3 and help us graph them. And then we label the axes with ticks and talks. So the waveform object is created with this wave JSON structure, and we call that waveform. Then we pull out from the Logic Tools overlay the pattern generator, so we get an instance of the pattern generator object. We initialize the trace analyzer with 16 samples, so our constant is 16. And then we set up the pattern generator itself, not the trace analyzer, but in particular the pattern generator with the wave JSON object, the stimulus group, and the analysis group named stimulus and analysis. Finally, we initialize the Boolean generator with the Logic Tools overlay. And then you can't see this at the moment, but we're going to connect the D0 to D19, D1 to D18, D2 to D17, and so on with the same wires we've used in the lab before. So now we come to the logic of the multiplexer in the Boolean generator. Let's take a moment to go back to the slides. In particular, we need to think about what is actually a multiplexer. It's nothing more than a complex logic function made out of gates. The data select inputs can be, in this case, one of four combos, but then that corresponds to the input selected, D0 through 3. So really, what we have is a logical expression for this particular combo, and then and whatever D0 is. So if D0 happens to be a 0, then these data select lines need to help that particular part of the multiplexer produce a 0. And then ultimately there's an OR that um, allows all the input lines, the four input lines, to become outputs through one channel. So the benefit of an OR is that it can have more than one input and then one output. So this multiplexer, that's the moment where the four lines join to one through the OR gate. Now, what this means is that we're going to have four terms in an SOP expression with joined by ORs, and then each of the little factors in the SOP expression are ANDed, of course, with each other using inverters where appropriate. So for example, S1 bar, S0 bar, and D0 would be the first term. And that's what you see here, only the problem is we can't have inputs be equal to outputs on the pink Z1 board. So we have to use a wire to connect the pattern generator to the Boolean generator. So the Boolean generator inputs are D19 through D16, and then D14 and D15 represent the most significant and least significant bit of the data select lines. So here we have 0, 0 due to the inverters, and then 0, 1, and then 0, 0, 1, and then 1, 0, and then finally 1, 1. So the placement of the inverters matters there. And then these are the data select lines, and they're ANDed. So we have the first, second, third, and fourth term in the logical expression for the multiplexer. Now, we would have liked to just OR all of these and then send the output to some observable, like, for example, an LED. However, we can't do that due to a technicality on the board, which is that all logic functions are created in a certain way in a lookup table. A lookup table is a way of generating all possible logic expressions given a certain number of inputs and outputs. And it turns out the maximum number of inputs for any one output is 5. We can have 1 to 5 individual pieces of data that flow into an output in the Boolean generator. This may sound surprising to you since we've done many examples with the Boolean generator, but if you think about it, we've only ever dealt with up to 4 inputs. Now we could have them in all kinds of wild and wacky combos, but the number of them has been 4 or less up to this point. So now we're doing 6 inputs because we have 2 data select lines plus 4 data input lines. And so the pattern generator will generate 6 outputs, and so we can't actually pipe all 6 to one Boolean function. So what I've chosen to do is to split the output between LED 0 and LED 1, so we have output 1 and 2. Now, our first function will be output 1 plus the first term or the second term, and so that'll be the first half of the 4 to 1 multiplexer output. And then the third or the fourth term will be the second half of the 4 to 1 multiplexer output. Notice that we create 2 functions in our multiplexer function dictionary that will go into the Boolean generator. And so we have multiplexer out 1 and multiplexer out 2 as their names. F and G are the actual logical expressions. And we set up the Boolean generator with the multiplexer object here. This is a dictionary of our functions. And then this will display the expressions. So what we're going to do is reset the kernel, and then we're going to wait for the kernel to be ready, run the code, wait till it's finished. All right, so we have our output. This is a fresh output. So mux out 1 is LD0 being set to this expression, 0, 0, and the data select line, or 0, 1, and this data select line, comma, and then we have the second half of the output, LD1, which is 1, 0, data select or data line, and then 1, 1 data line, and they're all ORed. So if we go down here, what we can do is run the logic tools controller. So we're pulling out that particular instance of that class from the logic tools overlay, and then in a loop of 16 items, we're going to step between the output of the Boolean generator and then the pattern generator. At the end, we'll show the results of the pattern generator trace analyzer. So that's in particular the data that is captured by the analysis group in the trace analyzer. All right, so here we go. We've got to go to the second cell here, execute. Should take about 16 seconds because there's 16 stages in the stepping, and then the Boolean is being evaluated, and I can see that the LEDs are flashing in the correct pattern on the board. So we're going to come back and take a look at that in the second half of the tutorial. So the pattern has been generated, and what you see is high, 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 but each data line is taking its turn. And so actually the LED, what it should be, if we're selecting 0, 1, 2, and 3, then the LED would be on the whole time, even though it's receiving data from 4 inputs, which could be on or off. It would be on, and then again on, on. So that would tell you if the LED is uninterrupted, that the data select lines are being used appropriately. In the meanwhile, we actually observe the real voltages that are coming out of our data lines, and they do indeed match the output of the pattern generator. So what we have to do now is go stop the Boolean generators and the pattern generator, and we're going to reset, and then in the second half of this tutorial, we're going to film the actual LED output to prove that it works properly. Stay tuned.
Hello again. So I'm about to execute the pattern generator, which will originate here, and then the multiplexer and Boolean logic is set up over on this side, and it'll turn on the LEDs in the correct pattern, assuming we don't have a loose data line. So here goes. So what you're seeing is that each LED has a duty cycle of 50%, but they're offset because we can't display all of the output on one LED because that would require 6 different inputs for the logic function. So what you saw there is that the first LED was on for 8 seconds and the second LED was on for 8 seconds, and they're interleaved. So that's just to show you that the function is working correctly and we've correctly implemented the multiplexer.